out that the first phase of this solution consists in reducing the matrix A to an upper triangular form, and the second phase was finding the individual unknowns by using a backward substitution. But as I told you before the break, backward substitution might be sequentially a nice idea, but doing in a parallel way is almost impossible. So we should reconsider the problem, and we should try to find another way out. So consider here this upper triangular form. Basically what we have to do is to find an inverse of this upper triangular form in order to find the unknowns x1 to xn. So that means we have to come up with a procedure for finding the inverse of such a triangular form, and that can be done in the following way. First, we compute the inverse of A by a so-called divide and conquer method. We met in one of the first lectures, and as I will show you in the next slides, that can be done in log square n amount of time and an O n to the power 3 amount of work. Then we compute x is equal to the inverse of A times B, assuming that A is triangular. That can be done in log n amounts of time and an O n square amount of work, and that is by the results we already obtained from matrix times vector multiplication. And that means that the total cost here equals log square n and an amount of work of O n to the power 3. And that's of course much faster than we would achieve by trying to simulate this backward substitution method. So this is an alternative for the backward substitution. And the most important step here is how to come up with an inverse A minus 1 for a triangular matrix. Well, assume that we have an upper triangular matrix, then the general form of such a matrix consists of a block here of arbitrary entries, here a block of arbitrary entries, here a block of arbitrary entries, and here a submatrix containing only zeros. From these submatrices, we also know that they should be upper triangular. If you have a block of zeros here, then this matrix should be upper triangular, this matrix should also be upper triangular in order for A to be upper triangular. Well, if you have such a matrix, then finding the inverse can be done quite easily. Because if you compute for such a matrix of this form, A1 and A3 are upper triangular, its inverse, that's a very easy computation, then it turns out that the inverse has a particular form. It's again an upper triangular matrix where A, this entry, is the inverse of an upper triangular matrix, A1. This is A, the inverse of an upper triangular matrix, times A2 times the inverse of an upper triangular matrix, and this again is the inverse of A3. Okay, well, that's an easy way to compute. What should be the case if you multiply A times the inverse of A is, well, these two, of course, give you the identity matrix. Then this one times that one gives you a 0. Then this one times the second one gives again you a 0. And so you end up with a complete identity matrix. Yeah. So, if you look carefully now, you see that what is needed here in order to give you the inverse of A is only computing the inverse of the first subblock and the inverse of the next subblock. Once you know them, you can compute the whole inverse, because this requires the inverse, this requires the inverse, and then times A2, you already had it. So, computing the inverse of A comes down to computing the inverse of a submatrix of A, here, A1 and A3, using the results and computing them, multiply them with the inverse, and then you have the origin. So, let's see. If you have the original A, you end up with finding the inverse of A1 and A3. A1 and A3 are again upper triangular, so you can pursue this computation in an iterative way to A1 and A3 separately, but of course concurrently. And again, consider A1 as a block of 4 matrices, again with 2 of these diagonal elements being upper triangular matrices, and iterate on them too. So, if you take the order of the matrices, well, then this is a matrix of n divided by 2 rows and n divided by 2 columns, and this one, for this one, the same. So if you would apply this procedure in a recursive way to the submatrices and end up finally with a matrix of size 2 by 2, in which you can find the inverse almost immediately, then it would, the number of operations, the total number of operations required would cost you, well, Wn is 2 times Wn divided by 2. You have to find 2 inverses, but each of half the size, plus On to the power 3. Well, why On to the power 3? You have to perform 2 matrix multiplications in order to recompute your original matrix. So, well, if you solve such a recurrence equation, then you end up with Wn is On to the power 3. Just do that. Okay, but if you take parallel time, then, well, you have to perform, if you have to find 2 inverses of matrices of half the size, you can do that concurrently. So Tn is Tn divided by 2 plus the O of log n, and the O of log n, of course, is needed to perform here 2 of these matrix multiplications in parallel time. So Tn is Tn divided by 2 plus log n. If you solve for it, it will require you log squared. And here you have your basic recursive algorithm for finding an inverse of an upper triangle matrix. Yes?
The recurrence relations for Tn,
yeah.
could that be solved with the master method?
Sorry?
The recurrence
Yeah,
relation?
yeah, yeah.
Okay.
Sure. Yeah. Well, yeah. Basically, what's the idea here? If you halve here your n, then you add a log n to it. Yeah. The next time you add a log n divided by 2 to it. This log n divided by 2 is upper bounded by log n. How many number of steps do you require before you have a constant? That's log n. So you have log n terms, each of size, at most log n, and that is log squared. Yeah? So everyone agrees that this is the basis for a recursive algorithm for computing an inverse of an upper triangular matrix. Yeah? And that gives you an enormous advantage compared to backwards substitution, because now indeed we achieved here a log n speed up. Okay, let's continue with the second topic I would like to discuss, and that's matrix multiplication for special cases. Here is the basis, the basic algorithm that we need for matrix multiplication, and that was in fact by doing parallel prefix computation steps. in this algorithm in order to come up with the entries Cij1, where the result of these prefix computations are stored, and these are transferred then into the final entries of the matrix. The total number of steps is in parallel time log n, and in sequential time O n to the power 3. Now what we would like to do is we would like to consider some special cases where, for example, we have to multiply Boolean matrices. Would that save us some computation time? And yes, we can, if we assume, of course, some special facilities for our processes, like we did, for example, for maximum computation. If you take the resulting computation for the elements Cij, then Cij is an OR of n's. It is AI1 and B1j, or AI2 and B2j, or etc. The OR of n's, of course, can be quite easily computed. How much time do you think computation of a single element of these Cij's would take if you perform it on, for example, a CRCW? Think of the summon algorithm that we met before. Basically what you have to discover is whether there is a 1 here in this expression. So if you apply here a CRCW and you investigate here all these n's separately, you only have to write a 1 if you discover that there is a 1. That would not give you any write conflicts. So in constant time, with an O n amount of work, we could find this Cij. But we can do that concurrently. So indeed, if we go from arbitrary matrices to Boolean matrices, then we can find the resulting matrix as the multiplication of two Boolean matrices in constant time with an O n 3 amount of work. Yeah? And the basic algorithm, of course, here is the following. Where here, in fact, we do the essential step that requires a CRCW for ijk between 1 and n, pi do if C prime ijk equals 1. So if there exists a 1 among them, then Cij should be equal to 1. And else it is 0. So, total computation time for each of the 3 steps is constant amount of time, and here an O n 3 n3 and O n 3 amount of work. So the total time indeed is constant, and the total number of operations is cubic. Okay, can we use this result to find, for example, a speed up for computing a power of a matrix? Well, let's first start with the general result. So suppose now that we don't have 2 arbitrary matrices to compute the multiplication of, but we have to find the power of a matrix, a to the power n. Well, we can do that in log m times n times n to the power 3 amount of work, and log m times log n amount of time. How? Well, this is the idea, and it is basically a very easy variant on the sequential algorithm that was taught to you in, well, maybe the first year, in order to come up with a very fast algorithm for finding powers of a certain number. If you have a number and you have to find its nth power, then, well, you can apply a very easy recursive algorithm that, well, first tries to come up with the result not for n but for n divided by 2, yeah? if you have the result for m divided by 2, then you can find in the next step the result for n. And there is one basic, well, the only complication is that if m is odd, well, then first you have to lower m, you have to half m minus 1, then you have to find the result, and then you have to perform another multiplication step. But here is the basic scheme of it. So if m equals 1, then you simply return a. If m is even, then first you start finding the power of a, m divided by 2, and you return, of course, z times z, and that's the power of a. But that's a to the power of m. Else, so if m is odd, then you return a times power a m minus 1. And then here the recursive step again. Now, looking at that algorithm, you might wonder whether this is indeed a fast algorithm, because, well, you might reason as follows. This would anyway cost you the O of m number of operations, because you might be extremely unlucky and you might have to perform this recursive branch an O n number of times. I can tell you that's not the case. Can anyone tell me how many times I have to perform this step? Or this step? How?
One time.
One. So what's the amount of time I need? So the number of times I need to perform this recursive step. So I only reduce n by 1. Do you know how it's related to m itself? To the way, the size of it. This is performed whenever a is odd. Yeah? If you think about it, then you might come up with an idea. Yeah?
Well, as long as it's not a power of 2, you might have to do it again at some point in the future.
Okay. As long as it's not a power of 2, that is related to the special bits in the binary representation of m. Can you tell me which bits?
Mainly if it is a power of 2, there will be only one bit there.
Yeah, okay. And if it's not a power of 2, how
Yeah.
many bits are there?
I'm not sure, but I think there will be more.
Okay,
Only
so
one.
what's the worst case you can imagine?
2 power k.
Yeah.
Isn't it just the amount of ones in the bit
Exactly. Exactly. So it's the number of ones that determines the number of times you have to apply this statement. Think of it. If you have 1, 1, 1, 1, then dividing it by 2 would give you ultimately again a 1. Again 1. So the number of ones here determines the number of times you have to apply this the statement, and that's of course log n number of times. And else you have a reduction with 2. So the total number of times you have to apply this procedure in order to end up with m equal to 1 is the O of log n. So am can be computed in log n iterations. Yeah? Well, whether or not this is a scalar or a matrix, that we don't care for. Because the only thing here that will differ is the amount of time we need to compute this result or this result. Whenever we have here a reduction step, if this is a scalar, if z is a scalar, then of course this is constant time. But if it is a matrix, as in our case, then we have to take care for the cost of such a multiplication step. Well, matrix multiplication will cost you in time log n, and in work a cubic amount of work. So, well, the total figures here are for the amount of work log n times n to the power 3 and log n times log n for the amount of time. So in a general case, this is the figure for the power of a matrix. But we can easily combine that with our previous result. If a n times n is a Boolean matrix, then we can perform matrix, then we can find the power of such a matrix a to the power m in O log n time. Because we can do Boolean matrix multiplication in constant time. So you have a very fast algorithm here for finding the power of a matrix. Okay. Let me give you a very small, let me give you a very small application of this kind of matrix multiplication, of finding the power of a matrix. Consider a directed graph. And now you have the problem that you would like to find in this directed graph, given a node, the set of nodes that is reachable from a certain node. So suppose that I start with node 1. I would like to know whether or not another node is reachable from that node in, well, at most n steps, or in general reachable by following some edges in the graph. Well, then I use the following technique. I represent my graph by an incidence matrix, a Boolean incidence matrix. And I hope, of course, to apply my results for Boolean matrices in such a way that I can find the solution to my reachability problem in a very fast way. So Bij, I assign it a 1 if Vi is connected to Vj by means of an edge in graph G. So I represent matrices I use matrices to represent the structure of the graph. Now the transitive closure of such a graph, and that's usually denoted by G star is VE star, that's defined as follows. An edge VW is an element of E star if either V is equal to W, so you can obtain W directly from V, or there is a directed path from V to W in G. Yeah. Okay. So I can follow the edges of my original graph. And now the problem is how to compute G star as fast as possible. And as fast as possible turns out via the incidence representation. So I would like to find an algorithm for computing B star very fast. If I have found B star, then of course I can find G star immediately. Okay. So how to come up with an algorithm for computing B star? Well, that requires some explanation and some observations. First of all, I take a power of B, and I take the kth power. And now my statement is that if I take the entries of Bk, so the ith entry, then it's equal to 1 if there exists a path of length k from Vi to Vj in G. So by finding the power of B, I can directly find path of a certain length. Bk corresponds to the path of length k. Well, the idea is that you can prove this result quite easily by applying induction. And the induction step goes as follows. There exists a path of length k plus 1 from Vi to Vj. If I can split that path in a path of length k, and the final step, that's performed by following an edge in the original graph. If I have a path of length k plus 1, then first I have a path of length k, and then finally a single step that's following an edge. So, there must exist a path of length k from Vi to Vm, for some node Vm of length k, and an edge from Vm to Vj. So that means Bmj must be equal to 1. Well, so that means there exists a path of length k plus 1 from Vi to Vj if there exists an m such that I can go from I to m in k steps and from m to j in one step. And this m can vary. It might be the first one, second one, third one, or the last one. So that means it is bk to the power k I1 times bi1j, or b to the power k I2, bi2j, or etc. But this, of course, is exactly a result of matrix multiplication, namely of b to the power k times b. So that means that b to the power k plus 1 contains all the information about path of length k plus 1. And that's, of course, then a proof by induction of the fact that bkij equals 1 if there exists a path of length k. So matrix powers contain information about the path of between the two nodes. Well, now I should continue. Doesn't help me. Oh, sorry. Yeah. So, we now know that there exists a simple path from Vi to Vj if there exists a path of length at most n minus 1 to Vi. Yes?
Would this be more efficient than using pointer jumper?
Yeah. Yeah. Sure. Because in pointer jumping, you are dependent upon the height of the tree. The tree does not need to be balanced always. So there exists a path of length n minus 1 from Vi to Vj. Why? Well, you know that we only have to discover whether or not two nodes are connected. That means there should be a simple path. A path should not contain cycles. What's the longest path in a graph containing n nodes? Well, that longest path can be of length at most n minus 1. Because any path that's longer should contain a cycle. So we only have to compute powers until b to the power n minus 1. And there exists a path of length at most n minus 1 from Vi to Vj if we have a k in 0 until n minus 1 such that b to the power k ij equals 1. It might be the w, that Vj equals Vi, then we have it immediately, or well, it might be that we have to compute b2, b3, etc. until bn minus 1. So, either if we take k equals to 0, then b to the power 0 is the identity matrix. So, either ij equals 1, or bij equals 1, or b to the power 2 ij equals 1, or b to the power n minus 1 ij equals 1. So, if we would compute the identity, the incidence matrix B star, then B star would be equal to I, or B to the power 2, or B to the power 3, or B to the power n minus 1. This is the expression for B star. But this, of course, would be very unfortunate because Now we have to compute b, then b squared, then b to the power 3, then b to the power n minus 1. And that would be some kind of inherent, again, sequential computation. You have to compute them all. Well, we can do it better. And that is the result of applying computation, of applying matrix computation to Boolean matrices. Take a Boolean matrix that's the OR of the identity matrix of B and B, so it's I or B, and multiply it with I or B. Then, well, that will be I or B, or B or B squared, and now you see that you can apply some idempotency laws. B or B equals B, yeah? And B or I, of course, gives you then I or B, so this reduces to I or B squared. Well, so this means that if you take k equals 2, you can also find it by taking I or B to the power 2. Well, if you apply this inductively, then I or B to the power k plus 1 is equal to I or B to the power k times I or B. That's I or B or B to the power k times I or B, and that simplifies. In the same way as this simplifies, because you have at various points, you have the identical terms here. B squared, B squared, B to the power 3, B to the power 3. They all simplify, and what you finally obtain is I or B squared or B to the power k plus 1. That means that I or B to the power k plus 1 is equal to this complete result. So if you take here I or B to the power n, then you end up with I or B or B to the power n, and that means that n minus 1 already is sufficient to give you the final result. So we can compute B star. Okay, that also seems that here. So the conclusion now is that since B star equals I or B to the power n minus 1, and I or B is Boolean, we now have a result that there exists a O n to the power 3 times log n amount of work and O log n amount of time algorithm to compute B star from B. And hence the reachability problem, if you concentrate on parallel algorithms, can be solved in O log n time using a parallel. And that's quite fast. Okay. Well, finally observe that this algorithm is not weakly optimal. There are very clever O n square sequential algorithms for reachability. So, unfortunately, we can solve it very fast, but it is not weakly optimal. Okay. I will give you the basic idea for solving linear recurrences, and the next topic is composed in such a way that we first present a very general technique for solving linear recurrences. We show that it is a generalization of the prefix computation method, and then we investigate some special cases like I showed you here for matrix multiplication. I will discuss during this lecture only the basic setup, and I leave it to you to study the special cases. And these are more or less consequences of this basic setup. First, let me show you what the problem is. So, what is a first order linear recurrence? Well, such a linear recurrence is a sequence of variables, and they are related via recurrences to their preceding variables. You start with an initial step where y1 is assigned a constant, b1, a given constant b1. But the remaining terms are all related to preceding variables. So yi equals ai yi minus 1 plus bi. Yeah? And that's for I between 2 and n. And again, ai and bi are known values, coefficients. The problem, of course, is to compute the values in such a sequence as fast as possible. And note that this is a strict generalization of the prefix computation that we mentioned before, because if you take these coefficients for the preceding variables as a constant, then you get immediately back a recurrence for a prefix computation. y1 equals b1, and then yi is a certain constant bi plus the sum of the preceding constants. Yeah? Okay. So prefix computations are a special case of these first order recurrences. This requires a trick solving. And the trick is that you apply a unfolding step in order to reduce the size of the unknowns you have to solve for. After you have applied this unfolding step, you end up with again a linear recurrence, but this linear recurrence only will contain half of the number of the variables you already have. Yeah. So let's do here an unfolding step, and that means that you, well, in order to find y2i, you apply 2 times the recurrence relationship. Yeah? So this is a2i by 2i minus 1 plus b2i. Then again an unfolding step, and here you come up with the final result. It is a2i times a2i minus 1, here an unknown, then a2i, b2i minus 1 plus b2i. And now the trick is you simply compute the multiplication here, and you assign it a new name, a prime I, and this is called b prime I. Yeah? Okay, what is the result? The result is a sequence, call it zi, of even terms of your original recurrence equation. And again, that's a recurrence equation. Z1 is b prime I, b prime 1, and zi equals a prime I times zi minus 1 plus b prime I, for I between 2 and n divided by 2. Yeah. So this unfolding step helps you to reduce the number of unknowns. Now, you might be, I think, that clever to remember in which situation we basically applied the same idea. And it was in the very first lecture. I showed you an example how to find cumulative frequencies. In this algorithm that we applied, we also reduced first the number of unknowns by halving the number of unknowns in each step, and then again expanding the number of unknowns we have to find by multiplication steps. So we had a recursive algorithm. The recursive algorithm, we first found the values of half of the unknowns, and then the remaining ones only by post-processing. Here we do the same. So the basic setup is we start with a sequence of n variables, we reduce it to a sequence of n divided by 2 variables. This is the reduction step. You can perform that an arbitrary number of times. So you can apply the same procedure to this set of unknowns again. So you can reduce this, then you can reduce that, etc. So you could, in principle, you could imagine that you could find solutions in this way for this set of unknowns, for half the number of the unknowns. If you have found half the number of unknowns, it's very easy to find a solution for all the unknowns. Because you know that if I is even, then yi equals zi divided by 2. If if I is odd in yi, then, well, it requires a simple expanding of your linear recurrence to come up with the value of the next term. And you know that zi minus 1 divided by 2 gives you the value of yi minus 1. You pre-multiply it with ai, you add bi, and there you are, you have found your yi. Yeah. And again, I1, of course, equals b. Yeah. It's a simple step. That's the same, basically the same step as we performed for finding the cumulative frequencies by this recursive algorithm. So, assume that we expand our, that we reduce our number of unknowns every time, then finally finding a constant number of unknowns, we can produce by expanding the original set of unknowns, the z ones, and then finally we go up and we find the resulting number of unknowns for y. And this gives rise to the following algorithm, and it's a completely recursive algorithm. If n equals 1, then you basically output I1. Then for I between 1 and n divided by 2, you first try to come up with the coefficients that belong to the reduced set of linear recurrences. And this reduced set is formed by a vector A prime and a vector B prime. Yeah? This you can give again as input to the same algorithm, linker. Linker is completely determined by the coefficients A and B, and now you find Z by A prime and B prime, applying a recursive step. And how to find the original terms? Well, if I is even, then this yi equals zi divided by 2. If it's odd, if it's equal to 1, then find it immediately, and else perform a post-processing step. Yeah? Okay. What's the amount of time we need? This will cost you constant amount of time, constant amount of work, constant amount of time, O n amount of work, because of the n multiplications. Then you have to apply here a reduction step. So the amount of time here is t n divided by 2. The amount of work is w divided by of n divided by 2. And in the final step, you can perform all operations concurrently. So it will cost you O1 amount of time and O n amount of work. If now you compute the final amount of time, then the final amount of time is t n divided by 2 plus O1, and Wn is Wn divided by 2 plus On. So, now you can guess what the result is. If you apply this recurrence, what will come out for the amount of time? That's the O of log n. And here,
And log
this
n.
is the amount.
And log n.
You can do better. Because, well you are right if you assume that every term is dominated by On, but in the second step you have On divided by 2, then On divided by 4, etc. And if you count that and you take the sum, then it ends up with the O of n. And we would like to have a smaller upper bound because we would like to convince people that we have a weakly optimal L. Yeah? So the result is an O log n amount of time and O n amount of work algorithm for solving an extension of the prefixal computations. Yeah? So basically what you have to remember is that although this these linear recurrences are a strict superset of prefix computation schemes, you can apply basically the same trick to them by this recurrence scheme and end up with the same work time complexity. Yeah. You should be aware that we can, this is an application, but you can easily come up with a generalization of this scheme where you don't have scalars but vectors and matrices. So you can have a linear recurrence, I1 equals B1, where this is a vector of coefficients, and yi equals AI by I minus 1 plus bi for I between 2 and n, where this is a matrix and this is a vector. You can apply basically the same algorithm, but now call it Matlin curve, and now Matlin curve gives you a way of solving these matrix linear recurrences in O log n times log n terminal time and O n times n to the power 3 sequential time. Why here log m time? Well, if you have here log n times log n amount of time, well, if you had scalars, it would cost you an amount of time log n, because the multiplications can be done in constant time. If, of course, here we have m times n matrices, then each matrix computation, multiplication will cost you an additional log n. Okay. So this is the final slide. Basically what's after here is a discussion of a series of special cases where you have to bother about, for example, the case where every of these coefficient matrices is the same, or is Boolean, or has another special characteristic, and this will influence your final computation. If there are any questions next time about it, then please ask me, and I will discuss it in the next lecture. Otherwise, I assume that everyone read and got the message, and I will leave it to you during my explanation. So please take care for the slides.